Hi there, how's it going? Terry Brown, Mechanical Engineering here with another video going through the solution to an engineering mechanics problem. So let's get into it. All right, so this is the problem this time. A beam with two sections connected together here. Yeah, so we've got this beam structure, some loads acting, and we're wanting to know what the reactions are at the support. Okay, so as you should know, the first step in doing any kind of analysis of rigid bodies in equilibrium requires us to draw the free body diagram. Okay, so before we get into that, what I'm going to do just firstly is just to go and have a quick look at the textbook. All right, so this is, if you're in my class at UTS, then you'll have your Canvas site set up something like this, and there's always the textbook reference to whatever it is that we're studying here. So you can always click on this link to take you to the textbook section, and you should do that. All right. The videos that you see on YouTube and even mine, even though they're a bit longer, leave out a lot of the detail that's covered in the textbook. All right? And there's some important things in there. Things like, what are the limitations of this formula that you're about to use? What are the assumptions that have been made in order to be able to apply this formula that you may be about to use to help you design something? All right, so always go and check in the textbook and find out what it is, the limitations of use of the formula and the assumptions that have been made. So in this particular problem, we're wanting to draw free body diagrams and to analyze the structure and to structural component and work out the reactions that are acting on it. So you need to get to know these supports. So if we just quickly go into the textbook here, so you may have access to an online ebook like this, or you might have a physical paper textbook, whatever it is, make sure you go and have a look at that. All right, so you can see in here under the chapter section, free body diagrams, the author here tells us a thorough understanding of how to draw free body diagrams is of primary importance for solving problems in mechanics. Okay? And doing these analyses is the key. It was one of the key steps for designing structural components. Right? You need to be able to do this. And as part of that, we need to be able to model the supports. Okay? So we've got connections between structural components and connections to the ground or other main parts of the structure or machine that we need to model and understand the forces and or moments that are being transmitted through those. And the thing that guides you, no matter what the support is, are these two statements here. Right? So if the support prevents the translation of a body in a given direction, normally my textbook looks a little bit better than this. The resolution's not great, but anyway, we'll carry on. Yeah, so the two key things that you need to pay attention to are these two things here. Right? So firstly, if the support prevents translation of a body in a given direction, then there must be a reaction force exerted on the body in the opposite direction. Okay, so here we see a roller that prevents this body above it, this end of the beam here, from being able to move downwards. So there must be this force opposite to react against that. And the other statement is if the support prevents rotation of a body, then a couple moment or a reaction moment is generated at that location. Okay. Conversely, if the body is free to move, so we can see here, this body is free for the roller support, is free to move backwards and forwards in that direction, right? Free to move horizontally. So here, we don't show a horizontal reaction force. Whereas in the pin connection, can't move in the horizontal, can't move this way, can't move vertically. Right? So we have two force components or an unknown force in an unknown direction, but no moment reaction here, right? Because it's free to rotate about the pin. And then if we move down a bit here, we can see if we have a fixed support. So if this support here prevents this body from moving upwards, we have a force. or upwards or downwards. A reaction force in the vertical direction. This support prevents the beam from moving in the horizontal direction, so we have a horizontal reaction force, and also it's prevented from rotating. Right? So if we have our beam like this, push it down, you can't rotate about the support. So there's a moment being generated in my right hand over here. If it's free to rotate, right, if I hold it loosely, or if I hold it like this, I can rotate it around easily enough, right? So in that case, there would be no moment reaction. If I squeeze tight and prevent that rotation, then a moment is generated. All right, so let's go back to our problem. Okay, so let's draw the free body diagram, and then after that, then we start solving for the unknown reactions at the support. Okay, so free body diagram first, draw a simple outline of the body that we're analysing, free from anything it's connected to. Okay, so here we're analysing the whole of the bent beam structure, and we're wanting to analyse or calculate what our reaction forces are here. Okay, so we don't show the support here. What we do show is the reactions that are generated by that support. All right, so we've got our loads applied, and at the support at A, we know that it's constrained from moving as a rigid body in the horizontal direction, so we have our horizontal reaction force. It's constrained from moving vertically, so we have our vertical reaction force. We need to put on some directions, so you can just put on both of them in the assumed positive direction, or you can look at the other forces that are acting and work out whether it should be going to the right or to the left, up or down. Okay, so if we look at, in this case, the only other forces that we've got acting are the 6 kilonewton force acting downwards, and this force here has a vertical component acting downwards. So for this to be in equilibrium, some of the forces in the vertical direction equal 0, this force needs to be acting upwards. And then if we consider the horizontal forces, some of the forces in the horizontal direction equal 0. The only applied force in the horizontal direction is this one over here. So the component of this will be acting to the right. So this force over here must be to the left. And then we have our moment reaction. We can see that these forces over here will be tending to rotate this thing around clockwise. So for this to be in equilibrium, some of the moments equal 0, then the moment reaction here must be anti-clockwise. So that's our free body diagram. And now that we have that, we can just go ahead and use our equations of equilibrium to solve for those unknown reactions. So some of the forces in the x direction, and if we assume to the right is positive, so we can do it like this, or we can write in our, show somewhere our coordinate system like this. So x to the right positive, y upwards positive. Then we start looking at our forces. So we have our minus RAX over here. The only other force in the x direction is the horizontal component of this 4 kilonewton force. So we put in that and use our trigonometry to work out that component. So that will be, if we consider this right angle triangle here, this 30 degrees is adjacent to this side here, so this will be 4 cos 30 degrees. It's going to the right, so put that in, it's positive, and they're the only two forces, so make that equal to 0. Do your maths and solve for RAX. Right, same thing for some of the forces in the vertical or y direction, equal to 0, up is positive. You have RAY at the left-hand end of the beam over here. We've got minus 6 coming down here. And then we've also got our vertical component of the force, 4 kilonewton force over here. Now, as I've said many times in other videos, what you might be tempted to do in drawing this component is to draw it looking like this. Drawing it out over here. Okay? Try to get out of the habit of doing that, because the problem with with putting your component force out over here is that it looks like it's acting way out here. So when we go to calculate moments about point A, we're going to look at this and say, hang on, how far is this from point A? Maybe, right? So instead of doing that, draw your component in there at its correct line of action. So you should be able to see that opposite side of that right angle triangle is the same as our component here. Right? So that's the opposite side of this little triangle. So the length of this component is 4 sine 30 degrees. So let's get rid of that guy and leave our component in the right spot. That's in the negative y direction, so minus 4 sine 30, all equal to 0, and we can now solve for our unknown reaction force, RAY. All right, so now we have some of the moments, taking anti-clockwise as positive, and if we have x and y defined like this, then strictly correct definition for a positive moment is anti-clockwise. Right? In a 2D problem, it doesn't matter if you assume clockwise is positive, but if you've got x and y defined like I've shown here, then to be strictly correct, anti-clockwise is positive. All right, so taking that, we have our moment reaction at A, put that in, so that'll be positive. Rotate on our free body diagram here, we put it in as anti-clockwise. If we put it in as clockwise, then that's not a problem. The only thing that will happen is that when you calculate your answer, if it should have been anti-clockwise and you put it as clockwise, then you'll get a negative answer. Yeah. Right? Assuming you do your algebra correctly. So the next one is the 6 kilonewton force up here. That's acting at a perpendicular distance from A, 1.5 meters. And I think you can see that that will be tending to rotate that beam clockwise about point A. So if I do this, hold it at A here, push down, that will rotate or tend to rotate in a clockwise direction. Yeah, and if you're not sure, just do what I've done here. Just grab pen, hold it at the point where you want to determine whether the force is causing a clockwise or anti-clockwise moment, and therefore positive or negative moment, and just push on the direction and see which way it goes. So the next one is we've got our force out the end here of 4 cos 30 degrees. So that's this horizontal component here. And its perpendicular distance from point A is this perpendicular distance that goes up here. So if we extend the line of action of that force, that's out here, like this. And so the perpendicular distance will be up there like that. What I've got drawn in green there is our perpendicular distance. And from our trigonometry over here, we can see this is a length of 1.5, this right angle triangle here. So this side here, this vertical distance here, is the opposite side in our triangle. So that'll be 1.5 sine 30. Now, which way is this tending to rotate about point A? If you're not sure, just grab something, hold it, and push in the direction. So it's going to rotate clockwise. Right? Rotate clockwise. So that will be the negative moment. All right. Is that it? No, not quite. We've got this vertical component here to deal with as well. Okay, so that also acts at some distance, some perpendicular distance from A. So if you put that in, 4 sine 30 is that force. What's its perpendicular distance? It'll be 1.5 plus 1.5 plus the bottom edge of this right angle triangle here. So that's the adjacent side to the 30 degrees. So that'll be 1.5 cos 30. So we can put that in. So the total distance, perpendicular distance of this vertical component from point A is 3 plus 1.5 cos 30. Is it going to be a positive or a negative moment? Again, grab hold of your pen or ruler or whatever you happen to have on hand push down, which way is it going to go? That's also going clockwise, right? Down goes clockwise. So that's another negative moment. All right, so that's all of our forces that cause a moment about point A. So we can put that equal to 0, do our sums, and calculate our reaction moment as 20.2 kilonewton meters. Note that throughout my solution, everywhere that I calculate a numerical value, I indicate what the units are for that. So that's it. Now we just summarise our answers, note our final answers at the end, and round up our answers to an appropriate number of significant figures. And usually for most engineering problems, 3 significant figures is plenty. Any more than that, and you're probably telling lies about how well you know with certainty the variation in these numbers. Right? So most input values into an engineering problem are plus or minus a few percent. So you can't know your answers that you calculate to any better than plus or minus a few percent. Okay, so writing here 3.464, for example, indicates that you think you know your answers to plus or minus 0.1 or 2%, right, which is simply not true. Okay, so that's the end of the problem. Hopefully that wasn't too long and laborious, and there was helpful detail in that solution to what's a pretty simple problem. You know, you can probably solve that in a few minutes, really. But I wanted to go through some of the fundamental concepts and things that you need to know in order to be able to do more difficult problems. All right, so that's it for now. If you like the way that I explain these problems in detail, please give the video a like and maybe even subscribe. Not for my benefit. I'm not getting any money out of doing these videos. All the money goes to YouTube. But you know, if you think other people might find these videos helpful, then clicking on the like and subscribing means that the YouTube algorithm will suggest it to more people, or suggest the video to more people. Anyway, that's it for now. Hope you go well with your engineering mechanics problem solving, and I'll see you in the next video.